In this video, we're going to look at word vectors. So we looked in the previous video at TF-IDF document vectors. Those vectors are as long as there are words in the vocabulary, usually around 50,000. So a TF-IDF vector for a document is going to have a length of 50,000. It's going to have 50,000 different values. Word vectors are a little different. They have a dense representation. So these vectors are usually going to be about 300 long. And a dense representation means that each individual index doesn't necessarily correspond to some known entity in the world or known feature in the world. It's just some kind of soup that we don't quite understand. These dense vectors are still very useful. So we can take a vector for a car, and that vector, even though we don't know what it means, that vector will be similar to the vector for truck, and both will be very different from the vector for boat. We can contrast this with looking at symbols. So the symbol for car and the symbol for truck, if we're using a symbol-based representation, are going to be different. And they're both going to be different from boat. But there isn't a sense in a symbol representation that car and truck are similar unless you explicitly state it so. Word vectors, on the other hand, are learned such that car and truck have similar representations. So let's look at how they're learned. Word vectors are learned such that for a given word, you can predict the words around it. So given a word's vector, you want to predict the other words that are in its window or around it. So one way to do this is through an algorithm that consists of a double for loop. So we initialize each vector. So we create a vector for each word and initialize it with some random value. Then we start our double for loop. So for each word in the set of documents, we look at all the words around it, maybe a window of size 5 on each side of the word. And for each of the words in that window, we change the vectors for W1 and W2 so that they're a little closer together. And then we move to the next word in the outer for loop and look at all the words in its window and keep doing this again and again. We repeat this double loop until we're happy that the word vectors have converged. One technical detail is that there are actually two vectors per word. And the reason for this is because in the skip-gram algorithm, which is what this is a variant of, you're actually predicting the words around a word. And if there's only one vector per word, the most likely word around a word would be the word itself. But that's a technical detail. And in fact, we're not going to have to implement this algorithm. We are going to use GenSim's algorithm to learn the vectors. In fact, we can also just download the vectors from Google. And we'll see both of those things in subsequent videos. But let's continue talking a little bit more about these learned word vectors. They have an internal structure somehow. So if you take the vector for Italy and subtract the vector for Rome, you get some other vector. And if you take the vector for France and subtract the vector for Paris, you get a vector. And those vectors are actually very similar to each other. So somehow these vectors are encoding countryness and capitalness. Likewise, if you take the vector for king and subtract the vector for queen, you get a vector very similar to if you take the vector for man and subtract the vector for woman. So somehow these vectors, just by encoding the words around each word, are getting at some sort of meaning. And in fact, analogies like this are one way they use to evaluate word vector algorithms. And this is how word vectors are different from document vectors.